Hi there, everyone. This is Ms. Page, and in this lesson, we are going to talk about how to use our knowledge of transformations to graph some rational functions. Not all rational functions can be graphed with this method. They do have to be written in a structure or format that allows us to clearly identify parameter values such as a, h, k, and 1 over b. So first we're going to talk about what we call the parent function of the family of rational functions. And here we see f of x equals 1 over x. That's the parent function that we call for the family we call rational functions. And so there are some key characteristics of this particular function that we can use when we are graphing using transformations. One is that because if x is equal to 0, that gives us a ratio of 1 over 0, which is undefined, meaning it doesn't equal a number value. That creates a vertical asymptote at x equals 0, which is our y-axis. So that's what we're seeing here when the function approaches the y-axis, both as it heads up and down on the two different pieces. That is where that is coming from. It also has what we call a horizontal asymptote at y equals 0, which is our x-axis. So the function also approaches our x-axis as it heads to the right. So it's getting closer to that x-axis, and as it heads to the left, it's getting closer to the x-axis, one piece from above and one piece from below. So we can actually transform those two asymptotes using our translations. So the vertical asymptote will move either left or right based on a horizontal translation, and our horizontal asymptote of y equals 0, our x-axis, will either move up or down based on a vertical translation. Then the other two key things that we can use are the fact that 1, 1 and negative 1, negative 1 are always going to be points, of course, on the parent function. If x is equal to 1, that gives us 1 over 1, which is equal to 1. That's where that's coming from. And if x is equal to negative 1, that gives us 1 divided by negative 1, which is negative 1. So that is giving us that point right there. So we can transform these 2 points pretty simply and easily using all of our transformations, whatever we have: reflections, stretches, compressions, and then also our translations. So that's what we will be doing. So what are the forms that we can use this particular method in? So if we have a rational function in a transformation form, it would either look like this. This is if we have an a parameter, an h and k, or it would look like this. And this is if we have a 1 over b parameter and an h and a k value. And so let's take a look at an example, because the rest of this is just describing what I was talking about, how we would graph using transformations using our parent function. So here in this example, we are going to graph the function, and then after we do that, we'll state the characteristics of the function. Once you get familiar with rational functions, it is actually often possible to state some of the characteristics that we're going to be talking about before you graph. But right now, based on our first lesson where we looked at graphs and characteristics and things like that of those graphs, it might be easier for us to do the graph first. So let's take a look at our function here, g of x. So we know this is a rational function, and knowing it's a rational function gives us an idea of some of its characteristics, such as vertical asymptote, horizontal asymptote, and 2 pieces, one on each side of each of the asymptotes. So here, what I would do is I would look at the structure, and I would determine my parameter values based on this structure. So this 1 right here would be my a value. So my a is 1. Being positive, so I have no reflection, and being a, it possibly can create a vertical stretch or compression, but being equal to 1, then it's not going to create either of those. So now I move on to h and k. Here, x by itself, of course, is interpreted as x minus 0. So that makes my h value 0. So in this case, I do not have a horizontal translation, no moving of left or right. This plus 4 here is my k value. So I do have a vertical translation, in this case, up those 4 units. So what does that mean about my graph? Remember those key characteristics of the graph. So we want to draw our axes, of course, first. And keeping in mind I am moving up 4 units, I want to make sure I've got enough room to move my asymptote up those 4 units. So I might want to drop my my x-axis down a little bit. Here's my y-axis. Well, maybe not quite there. Let's try that again. So I would start by drawing my asymptotes. Asymptotes always need to be drawn as dashed lines because that indicates that the points on those lines are not actually valid points that are part of the function. So solid means point is on the function or part of the function, and dashed means it's not. So what I'm looking at is understanding those 2 asymptotes, which are my axes, x equals 0 and y equals 0 for my y-axis and my x-axis. So because there is no horizontal translation, h equals 0, the y-axis is going to remain an asymptote. So I'm drawing here a dashed line, trying to anyways, on top of my y-axis. This is actually optional because the y-axis, there's already kind of a line there, so it's one of the exceptions. You don't have to necessarily draw a dashed line if an axis is one or both of your asymptotes. Now, my horizontal asymptote, which starts off as the x-axis, is going to move up 4 units. So it's moving up here to y equals 4. So that's where I would start there. So the next thing I would do, remember those 2 points that I was talking about, which were 1, 1 and -1, -1. Those are points that are on the parent function. So we can transform those using all of our transformations, and that will give us an idea of where the pieces of this new function's curve will be located relative to its asymptotes. So 1, 1, which starts off right here, that would only be if the only transformation we really have is a translation up 4 units. So it moves up 4 units to right here. And -1, -1, which would be right here, also moves up 4 units to right there. So we are looking at then a piece of our curve being in this top right area, and when we draw it, we want to draw the ends so that they are shown going towards those asymptotes, and then put arrows to indicate that the curve continues. And we do the same thing in this piece down here. So we show it approaching both asymptotes as it curves through our transformed points that used to be at 1, 1 and -1, -1. So it's not a fully detailed graph, but it gives us enough information to have an idea of what's going on with it. And that's what we'll be expected to do here for these. So now I'm going to take a look at these characteristics. When you're doing vertical and or horizontal asymptote, remember that they are equations of lines. So equations have at least one variable, an equal sign, and a number. In a vertical asymptote, you're looking at making sure you understand that it's defined by all of its x values. So all the x values on our vertical asymptote, which is here, are all 0. So that is x equals 0. For our horizontal asymptote, a horizontal line is defined by all of its y coordinate values. And our horizontal asymptote, which is there, all of its y values for all of its points are 4s. So that makes it y equals 4. When we go to do the domain, remember that we can take a look at our graph here and see that all of the points will have these x values here for this piece, and the other piece uses all these x values. The only x value that can't be used or isn't used is 0 because it creates an undefined ratio. So our domain as an inequality would be the set of all x's such that x is less than 0 or x is greater than 0. And as an interval, we have two sections or pieces of numbers. So from negative infinity to 0 in union with from 0 to infinity, with parentheses, because neither 0 is included nor can we include any type of infinity. Our range, which is our y values, it is defined by looking at, remember, all the y values for our points relative. Actually, this nice horizontal asymptote here kind of breaks up our range. So we're looking at here, these y values going with all the points to this piece of our curve, and these y values going with all the points on that piece of the curve. So we're looking at y values that are above or greater than this value, which remember was a 4, and also below or less than 4. So our range is an inequality with the set of all y's. Be careful, make sure you are using a y variable here, such that y is less than 4. Always start with your less than portion. Like an interval starts from least to greatest. We do the same thing with inequalities, least to greatest. So numbers less than 4 are smaller than numbers than greater than 4, or y is greater than 4. And then our intervals from negative infinity to 4 in union with from 4 to infinity. All right, so that completes that particular problem. Let's take a look at another example. So here we're looking at this function h of x. So again, as before, just kind of emphasizing but having some differences here in what's going on. We're going to determine our parameters first. So this -2 would be our a value. So because of that, we're going to get an x-axis reflection. And because the absolute value of -2 is 2, that's also going to give us a stretch with the factor of 2. And this +3, remember, is actually the opposite of an h value. So our h value is -3, which means we have a translation to the left 3 units. Because there's nothing added or subtracted after the ratio, that means that our k value is 0. So there is no vertical translation this time. All right, so here, now I'm going to draw in my axes. And I'm moving to the left, so I might want to push my y-axis a little bit to the right, just to give me a little bit more room on the left. And then those asymptotes is what I do next. Remember, they have to be dashed. So my vertical asymptote of my y-axis, which is x equals 0, is now going to shift to the left 3 units. So it's moving over here. Mostly. Yeah, I can get it a little better. There we go. And our horizontal asymptote of y equals 0, there's no vertical translation, so it's going to stay exactly where it is. So here my dashed line is optional because it's an axis. Then I'm going to transform those points. So 1, 1. So 1, 1, which starts here. So remember that you want to do reflections, stretches, and compressions first, and follow that with your translations to make sure that you're always getting the point in the right location. So between the stretch and the reflection, you can do either one of those first. It does not matter. So let's say I stretch first. My stretch factor is 2. So this vertical distance of 1 unit from the x-axis is going to stretch to a vertical distance of 2. And then it's going to reflect across the x-axis. So it's going to move down here to -2 or 2 below. And then that point will shift to the left 3 units, 1, 2, 3, and end up right here as its final resting place. So let's get rid of all of this, hopefully. All right, now looking at -1, 1, which start here. So -1, -1 is going to again stretch, but it's going to stretch from 1 unit below the x-axis to 2 units below. Then it's going to reflect across that x-axis, so now it's above the x-axis 2 units, and then it moves 3 to the left, 1, 2, 3, and its final resting place is right there. Let me get rid of all this work. There we go. Then I can draw in the 2 pieces of the curve, one on the left side. Make sure you remember those arrows, and one on the right side, where the 2 ends of the curve are pointing at the asymptotes, like so. So, writing out those characteristics. So again, vertical and horizontal asymptotes, remember, are equations. The vertical asymptote here is defined by its x values, which are all -3, so we get x equals -3. The horizontal asymptote is defined by all of its y values, which are all 0, so we get y equals 0. The domain is going to be all of the x values, and so we use all of the x values except for -3, where the function is undefined. And I didn't specifically mention that, but notice if I plug in -3 for x, -3 plus 3 is 0, and that gives us an undefined ratio with 0 in the denominator. So that's why -3 is not part of our domain. So we have the set of all x's such that x is less than -3 or x is greater than -3, and the corresponding interval notation. All right, and then our range. So with our range, we're looking at all of our y values. So the y values that correspond to the points are going to be all of the y's that are above and below our horizontal asymptote. So we're looking at the y's here that go with that piece. That gives us then the y's that are greater than 0. And then here, these y's all go with that piece where y values are less than 0. So we've got the set of all y's such that y is less than 0 or y is greater than 0, and the corresponding interval notation to finish up this problem. All right, so next we're going to give you guys a chance to try a practice problem. So pause the video here and try this problem. When you're ready, come back and we'll take a look at the answers. All right, so let's take a look at the answers here. There we go. So if yours, sorry, just checking something real quick, we're good. So if yours doesn't look like this, some of the things that you might want to take a look at are, did you create the correct, or get the correct h value? So remember, we'd have to take the opposite of minus or -2 to get h. So our h should be +2, which means that the translation is to the right. That's why our vertical asymptote is right here, which is at x equals 2, because all of the x coordinates on that line are 2's. You have no k value, or your k value is 0, similar to the last example. And then our domains, which sadly are not in set notation, and our range. So we'll just kind of fix that like so. All right, moving on. All right, we're back now to another example. Now this example is going to demonstrate what we need to do or make sure that we have if we're going to graph a rational function that has a 1/b value. So it has either a horizontal stretch or a horizontal compression, and maybe even a reflection across the y-axis. But the thing is, this can be a little tricky, so be careful when you're working with these, because this structure right here, we can figure out what the horizontal stretch or compression is, what the 1/b parameter is, but we will not get the correct h value, because if you look back at the structure of the denominator of this type of problem, the 1/b parameter actually has to be factored out in order to get the correct h value. So this 0.5 is a 1/2, so I'm basically factoring out this 1/2, and 1/2 times x is 1/2 x, so that would be 1x now. This will still be plus. So now I need to know, okay, well, what times 1/2 would give me 2, and that would be a 4. And so half of 4 is 2, or 1/2 times 4 is 2. So this right here is not what we look at. This is what we look at for the parameters to get the correct h value. So this right here, remember, would be our 1/b value. But we want b, which would be its reciprocal, which is 2. And since 2, the absolute value of 2 is 2, and that's greater than 1, that means we have a stretch. But our stretch is horizontal. So it's not a bad idea to remind yourself by writing that down. You've got a horizontal stretch, and 2 is your factor. The opposite of 4 now is our h, not the opposite of that 2. See how it changed? So our h is actually -4. So we're going left 4, not left 2. And then this -1 that's at the end, that is our k value. So we are going down 1 unit. So I'm going to draw in my axes here so I can get started with my graph. And down 1's not a big deal, so I'm just going to put my x-axis here pretty close to the middle. Left 4, I think I'll shift my y-axis to the right for some room. That's doing weird things. Let's try that again. Here we go. So now those asymptotes, dashed lines, remember? So our vertical asymptote, which is on the y-axis to begin with, is going to move left 4 units. So it ends up over here. And our horizontal asymptote, which starts out at the x-axis, it's going to move down 1 unit. So it's right there. So now I'm going to transform those 2 key points. So 1, 1. What is going to happen to 1, 1? So I would want to do my horizontal stretch first and then do my 2 translations. So my horizontal stretch, remember, takes this horizontal distance to the y-axis of 1 unit and multiplies it times my stretch factor, which is 2. So it stretches to a total of 2 units from that horizontal axis, or from the y-axis rather. And then let's get rid of this. So now it's here, and then it's going to translate. So it's going to move to the left 4 units. We're just counting 1, 2, 3, 4, and down 1. So it ends up right here as its final position. Get rid of some of this work. There we go. Then I've got -1, -1. Now -1, -1 is here. So we are first stretching this distance. So it stretches here, and then it moves left 4, 1, 2, 3, 4, and down 1. And so it ends up right there. I'm going to actually get rid of some of this work here so it's not quite so messy. All right, so it's stretched horizontally to the left, and then it's translated to end up right there. And then we can draw in our curve. There. And be careful here. Make sure that you're approaching your asymptotes, not your axes. I see that mistake a lot, and I do it sometimes too. Like I will see people who draw it so it goes towards the axis rather than your asymptotes. So the ends, the arrows point at those dashed lines. All right, to finish up the problem, our characteristics. So the vertical asymptote, which is here, defined again by all of its x values, which are all -4. So we get x equals -4. Horizontal asymptote, defined by all of its y values, which are all -1. So we get y equals -1. Domain, which is our x's, is going to be all of the x's except where we have that asymptote. So that's going to give us the set of all x's such that x is less than -4 or x is greater than -4. And then our interval notation to correspond. Our range is y's. So here are y's that correspond to our points for each piece of the curve are above and below that horizontal asymptote. So the only y value we don't have in our range is the y value here, which remember is a -1. So the range is the set of all y's such that y is less than -1 or y is greater than -1. And then the corresponding interval notation. All right. There's a practice problem here following for you to give a try. So here's your practice. Please pause the video and then come back when you're ready to compare with the answer. All right, let's take a look at the answer. So here we go. So if your graph doesn't look like this in some way, here are some key things that you should check to see what happens. So remember that this denominator, that if you used that, then you have the wrong h value because you have to factor out the 1/b value of 2 to create this form. And then the opposite of -3 is your h. So your h is +3, not +6. The other thing is, remember that by definition, that whatever this value is, that is by definition the parameter we call 1/b. So we have to take its reciprocal, and look at that reciprocal value before determining if we have a horizontal stretch or compression. So the reciprocal of 2 is 1/2. The absolute value of 1/2 being 1/2 and being less than 1 means that we have a horizontal compression. So that's what we're seeing here. That's why these points, instead of being 1 unit away from the vertical asymptote, are only 1/2 a unit. They've compressed to a distance of 1/2 a unit away from that asymptote. And then you have that +1, hopefully you saw that, which gives you your K value, and that gives you a translation up. So you're going right 3, that's why the vertical is there, up 1, so horizontal is at y = 1, and then your 2 points, they compressed by 1/2 a unit, or to a total distance of 1/2 a unit, since 1/2 times 1 is 1/2, and then they translated. All right, that finishes up this lesson, everyone, and I hope you have a great day.